The future of AI sets the stage for how specialized neural processing units, or NPUs, will drive next-generation capabilities. In this talk, we'll explore what NPUs do, why they matter for on-device intelligence, and how hardware, software, and systems design must evolve to make always-on, efficient AI practical for everyday devices and data centers alike. When we talk about understanding the NPU, imagine offloading heavy matrix math from a CPU or GPU to a purpose-built chip. NPUs accelerate convolutions and matrix multiplications, preserving battery life, speeding up inference, freeing main processors, and enabling responsive on-device AI for cameras and phones without constant cloud round trips. The core of an NPU is massive parallelism. Thousands of multiply-accumulate units paired with high-speed on-chip SRAM and dedicated data buses. This design maximizes data reuse and throughput, supports low-precision modes like INT8 as well as FP16 where needed, and often uses systolic or spatial arrays to deliver high TOPS with tiny power envelopes. Raw TOPS figures can be misleading unless you look at system-level design, and this slide shows why. Memory bandwidth, cache hierarchies, compiler optimizations, and model sparsity all shape effective throughput. So a well-designed 40 TOPS NPU with on-chip weights can outperform a starved 100 TOPS chip in real workloads. Comparing CPUs, GPUs, and NPUs highlights different trade-offs. CPUs excel at serial control, GPUs at high-precision parallel graphics, while NPUs target low-precision matrix math with deterministic latency and extreme power efficiency. In practice, NPUs can finish common inference tasks with a tiny fraction of the power a GPU draws, enabling always-on capabilities. The NPU ecosystem spans consumer edge devices, hyperscale racks, and niche architectures. On phones and PCs, vendors like Apple, Qualcomm, and Intel integrate neural engines. Data centers deploy dense NPU racks for training and inference, and specialized players explore wafer-scale or IPU designs, all expanding where and how NPUs are used. Defining an AI PC baseline, the Copilot Plus certification sets a practical hardware floor. Think of 40 TOPS NPU paired with 16 GB of RAM as the 2025 baseline. Beyond silicon, OEM on-die integration, assumed local acceleration, and a vibrant software ecosystem are all needed to foster next-generation AI applications on personal computers. NPUs bring intelligence to the edge, powering medical tablets for offline diagnostics, factory vision boxes for real-time defect detection, and remote field sensors for language translation or environmental monitoring. Key enablers for these deployments include fanny-less designs, wide temperature ranges, and secure boot to keep devices reliable and protected. Privacy-first AI becomes practical when NPUs enable local processing, deepfake detection, encrypted face unlock, and continuous behavioral analysis can all run on device. Keeping sensitive data local reduces breach liability and helps meet GDPR or HIPAA requirements, while millisecond responses deliver instant, secure decisions without cloud dependency. Low-power NPUs unlock always listening and offline productivity features by handling wake-word detection, speech-word text, and intent classification locally. That same efficiency enables instant meeting transcription, automated document summarization, and real-time language translation, turning devices into responsive, private digital coworkers without draining batteries. In industrial automation, NPUs enable real-time edge processing by analyzing images from industrial cameras, spotting micro cracks or faulty labels, and adjusting robots within a single frame cycle. The result is higher yield, reduced downtime through proactive maintenance, and data kept secure inside factory firewalls for compliance and speed. Developing NPUs faces fragmentation and optimization pain from proprietary vendor SDKs and missing universal intermediate representations. This landscape forces manual porting, increases engineering overhead, and slows adoption, creating a barrier to scalable software development and delaying time to marker for new AI applications. Feeding large transformer models is a major memory challenge because on-chip SRAM is limited and frequent. DRAM accesses create throughput caps. Techniques like INT4 quantization, sparse representations, and mixed precision caching help, while active research explores smarter hierarchies and caching to keep big models running efficiently on NPUs. Optimizing for NPUs means tuning, tiling, batching, and quantization while balancing performance and constraints. Many teams lack hardware-specific expertise, but emerging automated compilers and high-level frameworks are bridging that gap, reducing manual tuning and helping engineers trade off model accuracy, latency, and milliwatt budgets more effectively. Next-generation packages stack compute elements, general CPU cores, GPU tiles, and NPU arrays, connected by die-to-connex and unified memory. This approach enables dynamic migration of workloads to the most efficient element and coherent memory sharing, improving overall utilization and energy efficiency across mixed AI workloads. Research into new NPU architectures explores memoristive inner-memory processing and event-driven spiking neural networks. In-memory compute can slash data, movement, and energy use, while SNNs promise orders of magnitude savings for always-on perception tasks, though broader adoption depends on materials and engineering maturity. Treating NPUs as strategic assets supports greener, more secure AI ecosystems. Efficient NPUs can cut AI carbon footprints, enable local training inference chips, and reduce export dependency by guaranteeing supply chains. Building sovereign AI infrastructure with greener data centers and localized R&D strengthens security and sustainability at a national level. To accelerate NPU adoption, follow 4 pillars. First, adopt a hardware strategy that future-proofs silicon with 40+ TOPS demand. Second, invest in cross-platform software and drivers. Third, pilot edge AI applications to cut cloud costs and latency. And fourth, upskill teams in quantization and optimization to unlock full NPU potential.